we go. So all the stuff I'm speaking will be recorded. And I would also like to look into your eyes. Is it possible to switch on your cameras? Hey, hi.
Hello.
Hi.
Hey, that's great. So this way we can make a lecture that looks good. So Mr. Fabian Müllerschön and Alexander Friedl, are you also able to switch on your webcam?
Give me a second.
Okay, sure. Hey, Fabian. And Alexander Friedl, he is muted and the webcam is off. Is he here?
Yes, I'm here. Give me a second.
Yeah, don't worry, don't worry. So as you see, we are a very compact group. Um, in my software, I have a button to switch to a Rasteransicht. Was heißt das auf Englisch? A grid view of all the webcams. Do you have also some grid
Yes.
buttons so that you can see all of us?
Yes. Yep.
Hey, great. Okay. So I have also provided my slides. Do you see them switching?
Yes.
Okay. Technical test is also successful. It is indeed just the second screen of my computer. So I prepared that stuff so that we can switch forward and backward. Okay. So we will hear about semiconductor devices. So while I'm looking downwards, here's my iPad. And this iPad is put to the screen at my right-hand side. And this screen you see on your computer. So therefore, if I'm looking down, I'm looking to my iPad. And if I'm looking to the right-hand side, I'm seeing just what you see. Okay, so just interrupt me when something doesn't work like from your side expected. Preparations. You have perhaps already have taken a look to Relax, the Moodle system. I have just put my web browser to your screen. You have already taken a look into the script, so my slides. Have you all downloaded them? Great. I have just clicked on it and it is happening. Yeah, it works. So the second file, the A0, that's just a hobby of mine. I like something compact, one page, everything inside. So therefore, I'm making this one page, all slides in file. But yeah, if you like it, take it. If not, leave it. But very important to use during the lectures, as we all are sitting in front of the computers, please download and start also this table. If I call it table, it is the wrong word, the spreadsheet in English. This spreadsheet I have already downloaded and opened here. What is this spreadsheet? This spreadsheet is everything in my lectures for the semiconductor devices, all equations put into this in one spreadsheet and made all diagrams which I have used to prepare the lecture notes themselves. Therefore, this is the source of all these diagrams you can see in the lectures. Well, perhaps a more representative one, for instance, this one. the equations we will learn, we will derive them from the basics of the physics. And these equations are plotted with Excel, and the results are the slides. So the slides represent the physical background we will learn step by step. Melvin is coming. Okay. Hey, Melvin. I have now 3 Melvins. Melvin 1, Melvin 2, Melvin 3. Okay, let's see which of them is the correct one. So this is the 3rd student who is regularly listening to these lectures. Okay. So, Rauscha, Friedel, and Melvin, you are now in your 6th semester, right?
Yes, you are.
Okay, great. Hey, Melvin, I'm seeing you.
Hello.
Hey.
Hello.
Hi.
Sorry.
Also, sorry from my side. I've not immediately seen that you are waiting in the waiting room in the software. Okay, so I was just talking about the technical structure of our lectures, and you can all derive these topics also from Moodle Relax system. Okay. One moment. Yes. So some of you know me, and some of you don't know me. So I will just drop some words about my background, so that all are online in these lectures to whom you are talking and to whom you are listening all the time, hours by hours. So my name is Ertuğrul Sönmez. I'm originally from Turkey, but I have been born in Ulm, in the city, southern part of Germany. There also I went to school and the university, so I'm a local Ulm person. And at the university, I studied electrical engineering, and there the part which you call Vertiefungsfach, how you call Vertiefungsfach? Okay, the direction where you dive in more deeper is microelectronics. So what I'm teaching you was also my favorite topic during my studies of electrical engineering. So after studying electrical engineering, I have also got a researcher position at the university. I was 6 years researcher, so I have taken a lot of time to be a researcher. It was the best time before coming to Reutlingen. As a researcher there, I have designed integrated circuits using silicon germanium heterobipolar transistor technology. And why not silicon? Because if you combine silicon and germanium, you can make more high frequency devices using silicon substrates. And thereby, the very first 24 gigahertz integrated circuit has come up. That was 2000. So in 2000, the very first 24 gigahertz silicon-based integrated circuit was my PhD topic. And after having so much fun, 6 years, I went to industry, making ultra wideband IC design, and then came back to a group of who was a spin-off of the university. So all spin-off startup company. So I have been with a startup company called MicroGaN, GaN for gallium nitride. There we developed gallium nitride devices. So if you deal with, let's say, EPC gallium nitride devices, efficient power conversion from the US, we came up earlier with gallium nitride, but we got bankrupt because the venture capitals in Germany are not so sparkling like in US. We burned 10 million roughly. The EPC burned 90 million. So they have had more money from Google and co. So now you can buy the gallium nitride devices from EPC, and I'm lecturing it to you. So it's how it's Arbeitsteilung. Work division. No, if you divide up some tasks, so it is manufacturing, lecturing. Okay, so here we are. So if you want to ask me high frequency stuff or semiconductor stuff, also integrated circuit basics, so you can just drop these questions. Well, let's go back and start the lectures. Semiconductor devices. We will start the content from the charge to the transistor. So all the steps from having a charge somewhere to the device and how it works is the topic of the lecture. To give you a rough sketch of what is mentioned. Here you see an integrated circuit. This IC, by the way, I'm very proud about that. That was the 24 gigahertz IC, including the antennas. Here you see a 24 gigahertz IC on a footprint of 2 millimeters by 2 millimeters. So completely with a low noise amplifier, mixer, power amplifier for the transmit antenna, on local oscillator, and frequency divider. So the chip itself is here. So by the way, if you do research work in a European project, you also cooperate with European universities. So my colleague from the Uppsala University has designed these antennas for me. We co-integrated and produced them. So this is an IC on a footprint of 2 by 2. And in scale, here we have a single transistor. This transistor we have manufactured in microGaN as a single device, but this circuit here does operate at 3 volts. This circuit, this transistor can isolate 600 volt. This circuit has a current drain of 20 milliamperes, and through this transistor, if it is switched on, you can put through 20 amperes. So all is semiconductor. From which point of view you use it is the design and the physics beneath. You see all these fingers, all these strips. Is it visible? I think yes. So all these strips are single transistors. All these transistors are placed side by side, naming drain moment, drain source, drain source, drain source, and so on. And I can repeat that 100 times. So roughly 100 fingers are side by side. So you see, I have just written down drain source. Where is the control gate? In this picture, you don't see it. It is between drain source, and this drain source has, through the complete transistor, a gate control finger. This control finger just isolates the channel to switch off the device. So the purpose of this picture is there is not one semiconductor. So there are silicon semiconductors, also gallium nitride semiconductors. There's not one type of usage. If you have those small transistors here and also spiral inductors. Here, you can make an integrated circuit. And if you your purpose is not an IC, you make a big fat single device. Okay, let's go on. In these lecture notes, I have prepared millions of links to YouTube. Why? One of your former students, so former students have used some YouTube channels, and I have also taken a look into them, and I've seen it's pretty good. He's not talking too much crap, at least as much crap as I do. So you can take both and get more value than taking single of us. So all the YouTube videos I have spread into the slides. I have not asked him, so if you click 10,000 times on his YouTube video, he gets, I think, more money by by advertisement, but that's not my topic. So if you would like to view these videos, just do it. My favorite book, if you would like to take a look, is Mauro Zambuto, Semiconductor Devices. This is a very good written book with not so many equations, but it is, I think, from 1980. It's very old. If you are able to get it, you will get it used by Amazon or something like that. From today, take a look in any semiconductor device textbook, and you can also drop me a question whether it is useful for you or not. Okay, so the topics will be basics of semiconductor physics. So we will take a look on materials, and we will take a look on models. So bond models and band models. Why we will do this by models? If you take the crystal into your hand, you see some more transparent if the band gap is higher than the visible light, or some black stuff, or silicon is gray stuff. It is not transparent because the visible light is absorbed in the semiconductor material. So all these behaviors, optically, electrically, we don't understand by looking at it. We have to understand it by making assumptions and transferring these assumptions to theory and adapting it to the physical behavior of the material. So these models we will take a look step by step. At the end, we will know how carriers do the motion in the semiconductor. Why we need the carrier motion in equations? Because carrier motion is electrical current. And electrical current modification is all we do in circuits. What does a circuit do? A power electronic circuit switches on the current and switches off. An analog circuit does modulate the current as a function of the control signal. The control signal might be also a current or a voltage, doesn't mind. So all we do is modifying the motion of carriers. Therefore, we have to know that. If this is done, this is like in the evolution of the biology, then the cell, the single cell has been invented. Every step after the single cell is evolution of plants, animals, and so on. So if you have understand the models and the carrier motion, you can design any type of devices. And in this lecture, we will just take a look at the diode, at the MOSFET, and the bipolar junction transistor. Okay, so these are just 3 examples. You can replace them with JFETs, with IGBTs, and with dual gate cascode structured gallium arsenide high frequency FETs. So everything can be derived from the theory we will learn here. So put your most concentration on this area. If you don't understand here something, you will not understand fully the devices. Okay, that's all about the structure of the lecture. Now let's go to back to the spreadsheet. So Melvin, you have missed this topic in one moment. In the Relax course, we have a link called Vorlesungsbegleitende Unterlagen. There I have had prepared a spreadsheet in which all the equations of the lecture notes are in. And these lecture notes, this spreadsheet I have opened here. Just keep it prepared. I'm zooming out so that we see all the file at once. So you see I hope you see the yellow bars. These yellow bars are separating the topics in the lecture. So at the top, you see the topic name. I apologize in German. This stuff I haven't translated to English. I just forgot it. And the equations are marked here. And these equations are one by one the same as in the lecture notes. And the equations are plotted and made out of it a diagram. And these diagrams are all also in the lecture notes. So now let's go into the color scheme. One moment. So the blue figures, you should not change. Why? They are natural constants, or do you call it natural constants? I just opened the browser, open my favorite software, Naturkonstante. Yeah, return. Come on. You see, the advertisement is here, but the result of this translation is not here. Crap. Okay, you know what I mean.
But I think it is the natural constant. I think you're correct.
Constant.
Yes.
Oh, okay, thank you. That's the way you can help me.
Okay.
Just drop in and say it's correct or not, or give the right answer if you know it. Okay, so the natural constants are here: the Boltzmann constant, the elementary charge, the Boltzmann constant with different units. You can give 1 second. You can give these constants using joule per Kelvin or electron volt per Kelvin. So all these constants are there. And what you can change, or you could change, are in orange. But this orange field is a result of this field. And this field is a result of clicking on these arrows. If I click on it, you see the curve is updating. And what I have made there is you invent a new semiconductor with a different band gap. So you see what happens with this figure. At the moment, you don't know what the figure is, but that doesn't mind. We are talking about the structures. So this figure is calculated with this equation, and these equations result out there for different types of semiconductors. And you can say, okay, the gallium nitride semiconductor has, for instance, a band gap of 3.4, I think, 3.2. So the result you see here. Therefore, if you see an arrow, just click on it, try it out. And if you if you break the spreadsheet, just download it again. So don't worry about anything. So let's go on here about this section. This section is talking about the PN diet. So the PN diet, we will learn here. After we have made the basics, we are going to the PN diet. And these equations do talk about the space charge region, what it is, we will learn. And you can change the bias of the diet. So if you forward bias your silicon diet, you see some changes in the space charge region. You see some change also in the electrical field in the bipolar transistor. No, PN diet. And also, these curves represent the current the diet will give if you manufacture it concerning following the values you have typed in here. So here you have an orange area. Let's give the spreadsheet a second for just zooming. I've bought the fastest laptop you can buy for money, and Excel is able to stop working it. Now we have it. So here you see doping level. What doping level does mean, we will learn. So you are playing a semiconductor device manufacturer or designer, and the results are calculated and plotted there. Therefore, use this spreadsheet as often as possible, and if you understand that stuff, you can also answer all the questions I have put into the slides after each section. Therefore, theory in the slides, some textbook as you want, many links in the internet for YouTube videos, and calculations by spreadsheet. So use them all, and you don't need me then afterwards anymore. Go on. No, not you. Okay. Okay, so let's go back to the start. The semiconductor devices use semiconductors. What does semiconductor mean? It is not a conductor. It is not an isolator. It is a semiconductor. What is the specialty of a semiconductor? From a conductor, you cannot manipulate the conductivity, the specific resistivity of the metal. The metal has a specific conductivity, and it's it. That's it. It depends on the temperature. Yes, it depends on how fast you cool it down. So the crystallization processes does change a little bit the conductivity, but it is defined by physics. From the isolators, yeah, there is a certain range of conductivity, but you cannot say glass is a conductor. This is an isolator. But for semiconductors, you have a huge range for gallium arsenide, for silicon of conductivity. You can adjust it. And all the stuff humans can adjust is very interesting because then they can control it. They can put it into a way that it is useful for them. Semiconductors. And semiconductors have also an additional property, which is at the beginning intuitive, but you will understand why. For metals, if you increase the temperature, you increase their resistance. For semiconductors, if you increase the temperature, you decrease the resistance. For some types of them. For some other types, you increase the resistance. So you can have both using semiconductors. So there we will learn why this is the case. Okay, do you know the periodic tables? Let's see. Yes, I also play Clash, yes, but not today. Lectures. Here we are. I just have to increase the size of the screen. So if you take a look at the periodic table, now I'm missing the key here. I just use the mouse here. If you go to the group 4, we're at home. Here we are, silicon. What does group 4 mean? It has 4 valence electrons. What is the valence? It is the outermost shell of an atom. So if you have 4 outermost electrons in an atom, then you say you are in the group 4. So the carbon is also there, like silicon, germanium, tin, and then bismuth, and so on. So all these have 4 outermost electrons, valence electrons. If you have 4 valence electrons, and at the right-hand side, you see the Edelgas. Help me, Edelgas. Edelgas, so ein Scheiß. Das heißt Edelgas auf Englisch.
It's noble gases.
Noble gases, thank you, great. Yeah, noble. At the right-hand side, you see the noble gases. One moment. And what is the property of a noble gas? It has 8 outermost electrons. Why a noble gas is not ready to do electrical reactions is it is in the very best condition it can have from the energetic point of view. So it don't need any partners to go to a lower energetic value by doing chemical reactions. So therefore it's noble, it doesn't do any chemical reactions. And what does silicon do with having just 4 outermost electrons? It shares it with other silicon. And by sharing, you get a crystal. And the crystal has also a noble gas configuration. So therefore, we are, one second, no, not Clash today. We are on the way to make noble gases, noble configuration, also having transistors, no semiconductors from the group 4 in the periodic system. And you see, you know the crystal structure of carbon, it's diamond. And you know how hard and how stable, chemically stable carbon is. Therefore, we're in this area. But you can also make a crystal structure binary, ternary, or quaternary. What does that mean? If you combine 3 with 5 electron semiconductor, you can also get this noble gas configuration. That means gallium arsenide. Okay, gallium arsenide are high frequency semiconductor substrates. Gallium nitride. So my devices are gallium nitride. Your devices using in my thesis work will be gallium nitride from EPC, from California. You can also combine aluminum, indium, arsenide, phosphide. Many laser diodes are made of them. So the surface emitting laser diodes, just Google VCSELs, vertical cavity surface emitting diode, vertical cavity surface emitting diode, VCSELs. They have been somehow invented at the University of Ulm. They are laser diodes you can integrate onto a substrate and make many of them parallelly for mouses or for data transmissions. So these are the so-called quaternary semiconductors. But this lecture will use silicon. That's all. Here I went to the images of elements.com and have copy pasted some pictures of these elements. So I cannot hand it over, so you have the pictures. The silicon is this one. The germanium is this one. So you see these crystal structures. If you have silicon and have it the best purity silicon you can get and have very low temperature, it's isolating. If you heat it up, it just conducts a current a little bit. But if you put into boron into silicon, or if you put phosphor into silicon, then you can do what is meant by this range. You can adjust the specific resistance by just putting in impurities. Why? We will learn in the coming slides, in the next slides. So let's see. We have had 45 minutes recording. From my side, I'm in the flow, I can continue. What is from your side? Do you wish some break or just let's continue? For continue, thumbs up. For a break, thumbs down. Thumbs up. Okay, great. I will continue. Your fault. Coffee. This is from South Africa. from my earlier visit. And one moment. I'm very bad in remembering names. You in my at the left upper corner. Yeah, you, exactly you. Can you give me your name for all of us? So you're from South Africa, right?
Yes, hello, my name is David Botha. I'm from South Africa.
David, okay.
Yes.
I think it's also very good if all of you introduce yourselves Usually we do it at the beginning. My apologize. So continue. You with the yeah you. Yes, exactly.
I'm Tolgahan. I'm also Turkish. I live in Istanbul. I'm an ex-student for just 1 semester, and I'm here. Nice to meet you guys, and nice to meet you, Professor Ertuğrul.
Nice to meet you, Tolgahan. So you are in Istanbul at home, right?
Yeah.
Okay, so great. And the next is the Mickey Mouse with the microphone.
I guess that's me.
Yeah.
Hi everybody. My name is Matthias, and I'm one of the regular students in Reutlingen.
Okay.
Nice to meet you.
Hi, Matthias. So then the next one is Rausha, I think.
That was already me.
Ah, that was already you, right? Then Mr. Melvin, and last name is missing. Yeah, hi Melvin.
Hi. My name is Melvin Fernando. I'm 27 years old, and I'm from the Reutlingen University too. And yes, I'm looking forward for good Vorlesung. Also eine gute Vorlesung. Yeah.
Great. Alexander Friede?
Yes, it's me. I'm also a student from Reutlingen. Yeah, I'm study mechatronics with all the other guys here, and yeah, that's it.
Great. Okay, so you are talking about for all the other students, and
Yeah,
David Botta is in the center, right? David Botta is not here.
no, I think Fabian is still missing.
Yeah, Fabian is still missing.
Hi, can you hear me?
Yes.
I'm from Reutlingen too, and yes, my next semester is also in South Africa.
Yeah,
I hope.
Oh, that's very nice. What university are you going to there?
Stellenbosch University.
Oh, that's nice. I'm from Stellenbosch.
Yeah, nice.
So the world is small.
Just getting these connections.
Okay, and David Botta is not here, right?
That's me.
Ah, yeah, that's you. Then one more person is missing. Let's see.
I don't think so.
Okay. You don't think so?
No, we 7 participants.
Okay. No, then it's okay. Oh yeah, right, sure.
Please max out.
The next one is me. Okay, I have already introduced myself. Okay, great. So I have put that also into the row. Thank you very much for doing your self-introductions. Yeah. Go back to lecture. Lattice. So here we have a lattice. What is a lattice? A combination of atoms in a certain structure. If we have 4 equivalent bonds. So what is a bond? If 2 atoms share their electrons for one connection, this connection is called bond. So if I'm talking about bonding, I'm not talking about putting a wire on a semiconductor and making a strip for electrical connection. Here, if we talk about bonding, is we are making connections between atoms to form a crystal. And if these bonds are in a regular shape, then we get a regular structure called crystal. If it is not an irregular shape, it is amorphous, polycrystalline, so crystals but in broken configurations. But silicon semiconductors, or all semiconductors, require a monocrystalline structure. So ideally, all atoms, every single atom is in configuration in this shape. In the case of 4 valence atoms, all have a crystal structure of a diamond crystal structure. Okay, and diamond crystal structures, the bonds have an angle between them of 109.5 degree. Why? If they have this type of spreading, they have all these bonds have maximum distance to each other. Why maximum distance? Yeah, electrons tend to spread. So if they spread in these directions, they have the minimum energy, but they cannot leave because they are attracted from the atoms. This calculations is semiconductor physics. So we don't do semiconductor physics. Therefore, here we keep on doing that stuff on this level. Bonding, attraction, distraction, and regular combinations. So this is the crystal structure. So these types of bonds called covalent bonds. Covalent bonds are between atoms which have 4 outermost electrons, 4 valence electrons. You can imagine human beings are very lazy. So therefore, I have copied this picture from a book and colored it like a child. And this one, the basic bond picture, I have made it myself. So all easy stuff, you do it yourself. So therefore, we continue to work with the basic picture. So you just flat it down and emphasize the most important points in bonding. So if you have a silicon, this silicon has 4 own electrons, and each of them have 4 own electrons. And now I'm just marking the neighboring atoms. This one is not required. So the 4 neighboring atoms, and if all of them does share their electron with the neighboring silicon, all these silicon atoms have a noble gas configuration with 8 electrons. Therefore, the crystal structure in this way, having 4 covalent bonds for each atom, is very stable, chemically stable. Okay, for this topic, I have this link here below. Can I mark it? Can you mark this link below on the slide? And can one person of you just open the link and share your screen to us? Is it possible? Let's try. And meanwhile, I will make a galactic travel. So, galactic travel finished. Is somebody on the way of preparing? Yes? You see on your Zoom app a green arrow called share screen. Just try it. Is it possible? Is somebody trying?
I guess it's just possible if your screen is deactivated.
Okay, I will then stop it. I stopped it.
The link throws me an error. The link throws me an error, 405 error.
Oh, okay.
I guess I can do it.
I got the same error. I also got a 405 error.
Oh, okay. Then I have made a crap. Okay. Okay. I will go to the lecture notes. I will just share my screen again. Somehow. Now here we are. So screen is shared. Go to the lecture notes. I hope this link does work. I have no. The link is here. Can you try this link out? Does that work?
That link is working.
Hey, great. So then I will stop my screen sharing and give it over to you. Alexander Friedel, yeah, that's it. Now? Yeah, I see it. Okay, so I tried to go through these recordings of this guy, of Jordan Edmonds, and distributed these links to the lecture notes. And obviously, I have made an error in pasting it into the PDF file. So if you go back to the slides, and if you take
Can you
a look,
see now the slides?
Okay, I will go back to sharing mine. At least I will try. Has worked. So if you go back to the slides, you see a number here, 9. And this number should be the number of what you have seen in the link previously. Okay? And I will just take a look whether it's true. Yes, I just went to admin, to Jordan's playlist, and the number 9 is exactly what should have opened if you have clicked on it. Okay, so we have circumvent the bug at the moment. Okay, let's continue. There, I have prepared a different link from Wikipedia. There, the binding energy is also described very well. But what I want to explain to you here is the binding energy is the one which helps the atoms not just how is it called?
Drift away.
Hmm?
The atoms don't just drift away, they keep in position.
Drift away, exactly. Drifting, exactly. The cores of the atoms have positive charge, sure, and the electrons are not neutralizing them. And in a crystal structure, there are present all these nuclear cores. And these have the best energetic position if they have an infinite distance. Okay, and also for the electrons, they have, if the electrons from the binding point of view, vice versa, the bonding is better if the distance is very close. So the binding energy and the repulsion tendency of the nucleus cores, they counteract. So the binding tries to put the electrons, the atoms close in the lattice. And the cores tend to drift away in the electric field of them. And in between, we have an energetic minimum in a distance x between the atoms. So this can be calculated. We don't do it for sure. It's not our topic, but our topic is to understand why the crystals does exist. The crystals does exist because of the bonding energy, and the energy bonding level gives, together with the nucleus distraction, not attraction, distraction tendencies, the lattice constant. The lattice constant is a result. One moment, I see. I tried to open the chat screen. I didn't want to interrupt you, but I have to step out.
Yeah, it wasn't you.
Ah, okay.
I have to step out today quite a bit earlier.
Don't worry at all. My purpose is today also to make one lecture, and in the next week we will have 2 times lectures. So in the beginning, in the morning, 11:30 to 13 o'clock, and in the afternoon from 13:45 to 15:15. So
okay, I think you can just say it in the end, and I will talk to Melvin or Andreas Rauscher,
yeah,
Rauscher,
okay.
and yeah.
Don't worry, Alexander.
Okay. So see you next week.
See you. Bye bye.
Thanks for the lecture.
Don't worry. My pleasure.
Professor, I have one
Yes.
question. The distance, is that between the nucleus and the electron?
This distance is between 2 nucleus.
Oh, it's between 2 nucleus.
Exactly.
Okay.
So the nucleuses have the best position in terms of the positive charges of the nucleus itself in the infinity, and from the bonding, it's the 0 distance. Okay. Best bonding is in the 0 distance, and in between we have then the lattice constant. Okay. So then you can, yes, sure.
The bonding energy, is that between the nucleus and the electron? Is the bonding energy?
No, good question. Continue to place these type of questions. They are very basic. Bonding is the energy of having 2 electrons shared between 2 atoms.
Okay.
So this is the bonding energy. If I talk about bonding, I talk about this pair of electrons. And if you want to destroy a crystal, you have to destroy this bond.
Okay.
And therefore, in diamond lattice, no, in a diamond, because silicon has also a diamond lattice. Therefore, in diamond, so in a diamond lattice of carbon, so diamond, this bonding is very tough. So therefore, it is a very stiff crystal, stiff material. Okay, so this is then the distance between atoms, defined by the attraction of the valence electrons, by the bond. Okay. So now if you increase the temperature. What is temperature? Temperature is the movement of the cores. If you increase the movement, you increase the tendency to divergieren, auseinanderdriften, to move away. Okay.
To repel each other.
Repel, or repel?
Repulsion, repel, yes, repel.
Repel each other, right. Yeah. Therefore, if you increase the temperature, they repel each other more. And therefore, the crystal constant does increase. Therefore, your material grows. Okay. This is the nature of the crystal. I like it to have you as an English speaking person in my lectures. It's great.
That's good, yeah.
I like it. Okay, so we are in the bonding model, in the bond model, and we are now talking about intrinsic charge carrier concentration. I make it larger. Intrinsic charge carrier concentration. Let's talk about the words. What is intrinsic? What is your intrinsic motivation? Tell me your intrinsic motivation. What do you understand about intrinsic motivation?
I don't know.
Intrinsic motivation is the motivation you have on your own.
Inner motivation.
Without,
Inner motivation.
Inner motivation, exactly. Okay. So you have it in yourself. Nobody is pulling you. Nobody is distracting you. You have your intrinsic motivation. So this is the word intrinsic. In terms of semiconductors, the intrinsic charge is the charge which has the silicon on its own. If the silicon is pure silicon, so you have just silicon atoms, no other atoms are in. And the silicon itself has intrinsic charge carriers. Now, 2 minutes ago, I said the atoms have bonds. Therefore, we have a crystal. Now I say we have intrinsic charge carriers. What is the charge? The charge is only the movable electron,
free
the
one.
Movable charge. All other are not of interest if we talk about charge, because they are not movable. What do you talk about if you have something like this? So does it have a charge? No, it's something to dry something, yeah, but it has no charge. All electrons are bound. There are no movable one. Okay. We are interested in the movable ones. Why? If we move it, we will make current. And that's the purpose. We need current. So the intrinsic charge carrier is the electron. And the concentration of this is the number per unit volume. What is the, yeah?
Is it the amount of electrons that are free per,
exactly.
per volume?
Per volume. It's the number of charges which are free, which are freely movable in a unit volume. And the unit volume is 1 per square cubic centimeter. It is a common value in semiconductor physics. So if somebody tells my electron concentration is 1/16, it means that this crystal has 1/16 number of electrons in a cubic centimeter crystal. So if I name, if I give you a value in words, I give the value and the units is always per cubic centimeter. That's all. So from now on, per cubic centimeter. So let's talk about the carriers. I have the electron. If the electron was originally here as a bonding electron, now it is movable. It is in the crystal, freely moving. It has left its position. Before, this position was neutral. Now, this electron is on the way, and this position is 1 times positive charged. But this location is not fixed. What happens? This electron goes here in, and this position has moved. This electron moves here in, so then this position is positively charged. So if we have 1 freely movable electron, we have at the same time 1 freely movable hole. So these positive charges are called holes. Okay. Electron-hole pair is generated. Keep this in your mind. If we have an electron from a bond, we have at the same time a hole, which is freely movable. Now talk about concentrations. The intrinsic concentration is the number of electrons, or electrons is here, 1 second. Electrons is N0, and holes are P0. And as I said, the number of electrons, the concentration, is exactly the same of the concentration of the holes. And in combination, we name it intrinsic. So your intrinsic motivation to eat, nobody needs to tell you to eat. I'm hungry, so I'm talking about this intrinsic motivation. And the intrinsic charge carriers in a semiconductor is N index I, Ni, intrinsic carrier concentration. Therefore, I have written here charge, not electron, not hole, charge. Okay. After we have finished this slide, today we're over. So motivation, the next minutes. So the intrinsic charge level is a function of N0, P0, and square root of them. Why? Because each value is same. Okay. And this value is calculated by this equation. So this equation has something new. Now it starts to be partly theoretic, but I try to make it visualizable. Okay. The capital N is also a concentration, but not of charges. This NC and this NV is the number of places in a silicon for movable electrons. Okay. One moment. It is the effective density of states density of states that can be occupied by charge carriers in the respective band. We haven't started band, so I'm taking some words from later slides to today. Today I say the following. This is the maximum amount of freely movable electrons. More you cannot have. This is the maximum amount of holes you can have in the crystal per cubic centimeter. Yeah?
Just a question. So these things will always be the same except when the substrate is doped. That's when it starts getting complicated, because otherwise they're always the same.
These ones are natural constants.
Oh.
From the silicon. Let's go to the spreadsheet. I have put these values where I have put them down. I'm looking for them and don't find them.
They're on the left, or on the right there where you were just now. Just scroll left again.
Okay.
Right there.
Yeah. Thank you. Okay. Exactly. These are the values. This is the maximum number of electrons silicon can have. And this is the maximum number of holes silicon can have. Independently, doped, not doped, hot, cold, this is the maximum value.
But didn't we just say that if there's a hole, then there must be an electron pair, so they must always be the same?
Basically, yes, but okay. You have for the electrons more places.
Okay.
Why? It's a result of physical calculations. Oh. I haven't also taken a closer look at it. I have just taken these values as granted, okay. And I'm just using them.
Okay.
So we have certain amount of places, states, where the electrons can take place and move. Okay. So if we have these maximum values, and then we take an equation which uses the band gap, that's the energy you need to wrap these bonds away. So that's the band gap energy. And that's the Boltzmann constant. We learned that the Boltzmann constant is a natural constant, and it has a certain too much talk. Einheiten.
Unit.
What is
unit?
yeah, unit. My name is after all, yes, unit. It has a certain unit, and unit does make a relation between energy and temperature. So the Boltzmann constant gives you how much energy one particle has if it has a certain temperature.
Okay.
This relation is the Boltzmann constant. Therefore, going back to the equation, so if we have a certain temperature and combine it with the Boltzmann constant, then we have an energy. And if we have the energy to destroy the bonds, then we have a relation without a unit. Unit is 1. Then I can put it to the exponent of E. Then I have a factor. This factor, English, this factor gives me how much of this possible occupiable places for carriers are really occupied. So if we have a high temperature, then we have more occupied places, more movable charges. So the intrinsic carrier concentration is a function of a temperature. Yes, that's true. And then let's take a look at the plot, the spreadsheet. So I have now, I'm waiting for Excel for doing crap stuff. I don't know what. I just zoomed. I'm getting angry. You don't see it. Okay, now here we are. Now we have at the left-hand side the value, so the intrinsic charge carriers per cubic centimeter, in blue for silicon, and in orange for our artificial semiconductor, which we have adjusted by clicking on this arrow, you know? So just for remembering. And here we plot 1 over the temperature. Why 1 over the temperature? Because if we plot 1 over the temperature and plot it logarithmically, we have a linear function. Therefore, 1 over temperature. And if you want to see what the temperatures really are, you click on it. Okay, we click on it and we see the 1 over temperature and the Kelvin value at right-hand side. You see it? You can identify it? I hope so.
Yes.
Okay, great. So therefore, let's go to the room temperature, roughly 300 Kelvin. We have roughly, that's a wrong value. Ah, yeah, sure. We should take a look here. We have roughly 1 over 10 over 10 carriers, roughly. And if we go back to lectures, I can tell you the intrinsic charge carriers are at room temperature 1.5 times 10 over 10 per cubic centimeter. Now to get this into relation, I say this number of charges, although it is 10 over 10, is very low to calibrate your words, your qualitative words with the figures. 10 over 10 is a very low figure. 10 over 19 is a very high figure in semiconductors. So keep in mind, the intrinsic charge carriers negligible for carrier transport. Okay, so that's it. We have learned up to now that the stuff we are dealing with are silicon crystals. We have to understand why the crystals do have movable carriers, charges, why we are interested in the movable, but because the rest of them are also in the wood. We don't use wood for integrated circuits. We do use materials which have a controllable level of charge. That's the first step. That's all from me. Do you have questions?
Oh, I'm really impressed with the Excel sheet. It's very, very cool.
Oh, thank you.
Yeah.
It is also my hobby. It was my hobby to do that.
Oh, that's
Okay.
very cool. Thank you so much.
Thank you for listening and being patient with me. See you next week, the same time.
Bye-bye.
Mr. Selmetz,
Bye-bye.
Yes?
I've got a short question, but it's just, I think, for me and Melvin, because of the second lecture, Halbleiter Schaltungstechnik.
So all the rest which are not interested in Halbleiterschaltungstechnik can just drop off. Istanbul has also questions or not?
I'm in Reutlingen also.
So you're happy also?
Yeah, I'm a bit, but there will be a second lecture next week, right?
Yes. Next week, same time at 11:30.
I have another class at the same time. There is an overlap. So
Okay. I will record it.
Yeah.
And that's my very first recording today.
Mm-hmm.
And I will try. Theoretically, it should have worked, but I will find it out whether it has really worked or not.
Okay.
We will see.
Okay, thank you for
Okay,
the
then.
recording. I'm gonna use that so much.
Sure. Thank you.
Thank you.
See you for all the
Yeah.
rest who are not in circuits interested.
Bye-bye.
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 I will just stop also the recording, by the way. Stop. Aufzeichnen.